Okay, what we're going to do today is learn how to do ICE problems. What ICE stands for is equilibrium problems where you have an initial concentration, you have a change, and the E stands for equilibrium. I want you to notice the word that I highlighted in the problem, which is initial. I'll read the whole problem in a second, but you'll notice that this is a problem different from the problems we did yesterday where the concentrations that were given were at equilibrium. Because what's happening in this reaction is you just have the reactants like you do. We had the pop beads, we only had single atoms to begin with. Then the reaction starts, it goes back and forth until it reaches equilibrium. What we're going to do, let me read the problem. It says carbon monoxide and water are placed in a container and allowed to react and reach equilibrium. If the initial concentration, that's very, very important. Again, I encourage you to highlight that, of the reactants are 1 and 1, calculate the equilibrium concentrations of all species. And I've given a KEQ here. The first thing you're going to do when you're doing an ICE problem is you're going to make what's called an ICE table. I'm not even going to draw it with the lines. That's not important really, but we're going to make an ICE table. We're going to write ICE here. Again, I stands for initial concentration, and we can read that from the problem. It's 1 molar and 1 molar. Now, just like with your pop beads, you didn't have any A2 molecules to begin. When you add those reactants together, we don't have any product yet. So our initial concentration of the products is 0. Okay, how much is the change? One of the questions on your equilibrium packet that you did with the graphs was getting you to see and notice the mole ratio. So it's a 1 to 1 to 1 ratio. So let's say that the amount of carbon monoxide goes down by some amount which we're going to call X. Because the ratio of carbon monoxide to water is 1 to 1, this is going to go down by the same amount. Also, we have a 1 to 1 ratio over here. So this is going to go up by the same amount, as is this. Then the last row of the ICE table is to just put those things together. So here we have 1.00 minus X, 1.00 minus X, and X. That's the chemistry part of it. The next part of it is really just the algebra part of it. So what we're going to do is we're going to set up the equilibrium expression. So remember, I'll write the whole equilibrium expression out just so that you could review. So KEQ is equal to the concentration of the products over the concentration of the reactants raised to the power, we'll put on the bottom here, we'll put CO and H2O. And then I'm going to fill in the numbers there. So what do we have here? Well, numbers are variables. So we have X, and then we have 1 minus X and 1 minus X. And I'm definitely running out of room here, but that's going to be equal to the equilibrium constant, which is 5.10. Now again, the rest is just algebra. So let me scoot this up so you can see. What you need to notice about this, which is going to make your life a whole lot easier, is you need to notice that the numerator and the denominator are perfect squares, because otherwise the algebra gets more complicated. So what I'm going to do is I'm going to take the square root of both sides. So we get X over 1 minus X equals 2.25. And then I'm going to multiply both sides by 1 minus X. And I'm going to get that X is equal to 2.25 minus 2.25X. And X is equal to 0.692. We're not quite done with the problem yet, because if you look here in the last sentence of the problem, it says calculate the equilibrium concentrations of all species. Okay, so what do we have? I have that CO is equal to H2O, and that's equal to 1 minus X, so that's going to be equal to, I don't have a lot of room here, so I'm going to just put the answer, 0.31. And CO2 is equal to H2, and that's equal to 0.692. So I'm going to do 2 more problems with you, which the chemistry is really going to be the same in the setup. The difference is just going to be in the complexity of the algebra. Okay, so again, you can pause this video, you can email me if you have any questions, but that is how you do an ICE problem. And again, the important thing when you're taking your assessment on this, when you're reading the problem, is to notice, do the concentrations list initial concentrations or equilibrium concentrations, because those are very different. Okay, let's go on to our second problem. Let me scoot that down. Okay, H2 and O2 are placed in a container and allowed to react and reach equilibrium. If the initial concentrations of the reactants are H2 is 2, F2 is 3, calculate the equilibrium concentrations of all species. And I've listed the equilibrium constant there. Okay, we're going to first thing set up the ICE table. Okay, so H2 is 2.00, F2 is 3.00, because initially, and again, I'm going to do this, I'm not going to take off on it, but just as a reminder to you, it hasn't started yet, so we don't have any product. This is going to go by some amount we call X. This is going to go down by the same amount. Now, this is really important because this is our first experience with this. You notice, because the mole ratio is 1 to 2, however many moles this goes down, this is going to go down by twice that amount. And then I'm going to just combine this. Okay, so now we've set up our ICE table. We're going to plug it into the equilibrium expression. So we're going to say KEQ, which is equal to 115, equals the products, which is HF, that's 2X. Now remember, when we're setting up the equilibrium expression, it's raised to the power of the coefficient. I like to call that the double whammy. So we have a 2 here, but then we also have a 2 as the exponent. Okay, and then the reactants. Hopefully you're starting to see that this is going to get a little bit more complicated. If you like algebra, you'll love this one. Okay, so what are we going to do? We're going to say this is equal to 4x squared. By the way, I have done this for a long time, and students always, oftentimes when they get rid of those parentheses, they forget to square the 2, so don't forget to do that. Then, to get this simplified, we're going to FOIL it. So we are going to get 6 minus 5x plus x squared. And I'm going to go ahead and if you guys don't mind, I'm not going to take the time to do all the algebra because I feel like you can do that yourself. But if you rearrange and combine terms and all that, what we're going to get is 111x squared minus 575x plus 690 equals 0. And you probably got a little bit of a snapshot into how we're going to solve this, so I've given you the quadratic equation. Many of you are really good in your graphing calculators and you have a solver function in the equation. I don't even know where it is, but you have a way to solve it on your graphing calculator. But just a reminder, you might not have done this for a while. So this is A, this is B, this is C. And I'm not going to take the time to do that, but if you're going to plug it into the quadratic equation, you're going to solve and you're going to get x is equal to 3.29 or 1.88. Now here's the problem. How is that possible that we have two answers? I have never done an ICE problem where one of the answers isn't ridiculous and can be thrown out. Well, what does a ridiculous number look like? Let's take a look at what our concentrations are supposed to be. H is supposed to be 2 minus x. How can we possibly have 2 minus 3.29? How can we have a negative concentration? So we know that we can drop this one out. Okay, then to finish the problem, we just need to plug in for what we know. So I'll move this down here. X is equal to 1.88. H2 is equal to 2.00 minus x, which is going to be 0.11 or maybe 0.12. F2 is going to be 3 minus x. Don't forget about sig figs, which that's going to be 1.12. And then HF is 2x and that's going to be 3.776. So that's what you need to do to complete the problem. So the chemistry of it is exactly the same. It's just sometimes it gets more complicated when you're doing the algebra. And this last one is even going to be more complicated. All right, let's read the problem. It says NaCl is placed in a container and it is allowed to decompose and reach equilibrium. If the initial concentration of the reactant is 0.5, calculate the equilibrium concentrations of all species. Once again, we start with the ICE table. Okay, it seems like it's easier because we only have one reactant. However, that's not the case. You'll see in a couple minutes here. Okay, are you guys good with that? Remember, pause the video if you need to process a little bit or if I'm going too fast. Now, we're going to say that instead of this going down by x, I'm going to say it goes down by 2x because the coefficient there is 2. So this is going to be 0.50 minus 2x. This is going to go up by x. That's going to go up by x. Now let's plug that into the equilibrium expression. I'm going to scoot this up a little bit here. KEQ, which is 1.6 times 10 to the negative fifth, equals x times x. Oh, I made a mistake here. Did you guys recognize the mistake I made? Notice the coefficient here is 2, so this has to be 2x, and this has to be 2x as well. So we're going to say, I'll just put the 2 here, x squared over 0.50 minus 2x, and we have to square that as well. So if I simplify this, you'll see that I'll have 4x cubed in the numerator. All right, now, you guys aren't going to like this very much, but let me tell you how I'm going to solve it. You notice that in the numerator here, it would end up being 4x squared times x, which is 4x cubed. And you probably are better than I am in solving a cubic equation. I don't know how to do that, but here's what I want you to notice. Notice the size of the equilibrium constant. It has a negative fifth exponent, which is very small. What is that saying? If the equilibrium constant is products over reactants, and it's very small, do we have more products or more reactants? Okay, excellent. So what that means is barely any of it is going to go to products. And I'm going to argue that the amount that it loses here to turn into products is negligible. What negligible means, it's very small in comparison to the 0.5. It's like saying a nickel to Bill Gates. Yes, a nickel is 5 cents. However, it's negligible. It's meaningless to Bill Gates. Okay, now so I'm going to drop that 2x because it's so small, but why can't I drop this x if it's small? Well, I want you to think about that mathematically. If I have a big number, like say 1,000,000, and I add a really negligible small number to it, like 1,000,000, and I add 1 to it, it's not going to change the magnitude, or 0.01. It's not going to change the magnitude of it very much. However, if I have a big number like 1,000,000, and I multiply it by 0.01, you see that's going to influence that million more. So when we're multiplying by a small number, it is going to change things, but when we're adding or subtracting, we can just drop that. So let me just review one more time because I'm afraid that this all went kind of fast. Hopefully you realize that I'm not mean enough to ask you to solve a cubic function, but you do notice that the equilibrium constant here is really small. Since it's products over reactants, that means that barely any of it is going to go in the forward direction. In fact, so little of it that it has the products over reactants ends up being to the negative fifth. So I'm going to say, I call this just the chemistry razzle-dazzle. So I'm going to say 1.6 times 10 to the negative fifth is approximately equal to, well, in the numerator here we have 4x cubed. And I'm saying that this x is so small compared to this that I'm just going to drop it. So I'm going to say that's 0.50 squared. Okay, and then, oops, did I forget something? Hold on, hopefully you're checking. This should be a cubed here, right? So I'm going to do a couple steps at one time. I'm going to get that x cubed equals 1.6 times 10 to the negative fifth times 0.50 squared divided by 4. Okay, and x is going to be equal to 1.0 times 10 to the negative second, if you want to do it in scientific notation. And now remember, the final step is plugging it all back into the last line of the ICE table. So the NOCl, I'm going to run out of room here. NOCl, would you might prefer to put that into regular notation, so it's going to be 0.01, right? So this is going to be, the NO is going to be 0.48 because it's 0.50 minus 2x. The Cl2 is just going to be x, so that's going to be 0.010. And the NO is going to be 2 times x, so that's going to be 0.020. Well, that's it. All the ICE problems, you look at the problem, you recognize that it says initial concentrations. That will prompt you to set up the ICE, what I'm calling an ICE table, even though it doesn't necessarily have lines in it. And then there's various ways that you're going to solve for x, and then finally you're going to plug it back in and find out what those actual concentrations are at equilibrium. Because this is a video, it might be helpful to replay it a couple times, pause it, try to solve it yourself, see if you have the correct answer, and if you have any questions, you can always email me.